Hi everyone, welcome back. In this video, we are going to discuss the top Java multithreading interview questions and answers. Let's begin. What is a thread in Java? A thread in Java is the smallest unit of execution within a process. It represents a separate path of execution, allowing multiple tasks to run concurrently within the same program. Every Java program starts with at least one thread, the main thread, and additional threads can be created to perform tasks like computations, I/O operations, network calls, or background processing. Threads share the same memory space of the process, which makes communication between them easy. However, this shared memory also introduces challenges like inconsistent states and race conditions if not managed properly. Java provides two primary ways to create threads: extending the thread class or implementing the runnable interface. Both approaches allow developers to define custom behavior by overriding the run method. Multithreading improves performance by utilizing CPU cores efficiently, reducing waiting time for tasks such as file access or database queries, and making applications more responsive. However, multithreading also requires careful synchronization and coordination to avoid concurrency issues. Next, what is the difference between a process and a thread? A process is an independent program with its own memory, space, resources, and execution environment. It is isolated from other processes, meaning one process cannot directly access another process's memory. This isolation provides safety and stability, but increases overhead because each process requires its own memory and execution context. A thread, on the other hand, is a lightweight unit of execution that exists within a process. Multiple threads inside a process share the same memory and resources, including variables and open files. This makes thread communication much faster compared to processes. Because threads share memory, they are more efficient but require synchronization to prevent data corruption. Processes provide heavy isolation and high stability, but with more resource consumption. Threads provide fast communication and scalability, but require careful handling of shared data. Java applications use multithreading to improve performance, responsiveness, and parallel execution, especially on multi-core systems. Next, what is context switching in multithreading? Context switching occurs when the CPU switches from executing one thread to another. Since multiple threads share CPU time, the operating system must pause the current thread, save its execution state, and load the saved state of another thread. This creates the illusion that threads run simultaneously, even though the CPU executes one at a time per core. Context switching allows multiple threads to make progress, but it comes at a performance cost. Saving and restoring states consumes CPU cycles, and excessive context switching can degrade system performance. This usually occurs when too many threads compete for limited CPU cores. In Java, thread scheduling and context switching are handled by the operating system. Developers must design applications in a way that reduces unnecessary thread creation and promotes efficient workloads. Using thread pools, minimizing blocking operations, and avoiding unnecessary synchronization help reduce context switching and improve overall performance. Next, what is thread lifecycle in Java? A thread in Java goes through several well-defined states throughout its lifetime. When a thread object is created, it begins in the new state. After calling the start method, it moves to the runnable state, where it is eligible to run but not necessarily running at every moment. Depending on CPU scheduling, the thread alternates between running and waiting for processor time. A runnable thread may enter the blocked state if it attempts to acquire a lock held by another thread. It may also enter the waiting state when it waits indefinitely for another thread's action, such as calling wait or join. If it waits for a fixed period, it enters timed_waiting. Once the run method finishes execution, the thread transitions to the terminated state. Understanding these states is essential for debugging multi-threaded programs because unexpected transitions often indicate deadlocks, missing notifications, or synchronization issues. Next, what is synchronization in Java and why is it needed? Synchronization in Java is a mechanism that ensures only one thread accesses a shared resource at a time. It prevents race conditions, data inconsistency, and unpredictable behavior caused when multiple threads modify shared data simultaneously. In Java, synchronization is typically achieved using the synchronized keyword on methods or code blocks. When a thread enters a synchronized section, it acquires a lock, also known as a monitor, on the object. No other thread can enter a synchronized block on the same object until the lock is released. This guarantees exclusive access and maintains data consistency. Without synchronization, threads may read stale data, overwrite each other's changes, or leave shared objects in corrupted states. Synchronization is essential for multi-threaded applications that involve shared variables, shared collections, or operations requiring atomicity. However, excessive synchronization can reduce performance because it increases blocking and context switching. Therefore, developers must synchronize only the necessary parts of code and use alternatives like locks, atomic classes, or concurrent collections whenever appropriate. Next question. What is a deadlock and how can it occur in Java? A deadlock occurs when two or more threads are blocked forever because each thread is waiting for a resource held by another. In simpler words, thread A holds lock 1 and waits for lock 2, while thread B holds lock 2 and waits for lock 1. Since neither thread can proceed, the program becomes stuck. Deadlocks commonly occur when multiple locks are acquired in an inconsistent order. For example, if one thread locks resource A first and then resource B, while another locks resource B first and then resource A circular dependency can form. Deadlocks can also arise from poorly designed synchronized blocks, nested locks, and long-running operations inside synchronized regions. To avoid deadlocks, developers must ensure a consistent lock acquisition order, reduce the use of nested locks, and minimize synchronization duration. Tools like threaddumps, profilers, and Java Visual VM help detect deadlocks in running applications. Next, what is a race condition in multithreading? A race condition occurs when the output of a program depends on the unpredictable timing of multiple threads accessing or modifying shared data. When two threads attempt to update the same variable simultaneously without proper synchronization, the final result becomes inconsistent or incorrect. For example, if two threads increment a shared counter at the same time, both may read the same initial value and write back incorrect results. This happens because read and write instructions are not atomic and can interleave unpredictably. Race conditions lead to bugs that are extremely difficult to reproduce because they depend on thread scheduling. Preventing race conditions requires using synchronized blocks, locks, or atomic classes, like atomic integer. Developers must ensure that all shared state is accessed in a thread-safe manner. Understanding race conditions is critical because they can silently corrupt data, cause incorrect results, and destabilize complex applications. Next question. What is the difference between synchronized methods and synchronized blocks? A synchronized method locks the entire method, meaning only one thread can execute it on a given object at a time. This approach is simple but can block threads unnecessarily if only a small part of the method accesses shared data. A synchronized block allows developers to lock only a specific section of code. It provides more granular control and uses a specific object as the lock. This improves performance by reducing the time a thread holds the lock. For example, if only 2 or 3 lines inside a long method modify shared state, synchronizing the entire method would waste CPU time and cause excessive blocking. Synchronized blocks offer flexibility because developers can choose different locks for different critical sections, avoiding bottlenecks. However, improper locking or inconsistent lock usage can cause race conditions or deadlocks. Next question. What is the difference between wait, sleep, and yield? The wait, sleep, and yield methods control thread behavior but serve fundamentally different purposes. The wait method is used for inter-thread communication and must be called inside a synchronized block. When a thread calls wait, it releases the lock it holds and enters the waiting state until another thread calls notify or notify all. This mechanism allows threads to coordinate work safely. In contrast, sleep is used to pause the current thread for a specified time. It does not release any lock the thread holds. Sleep is often used to simulate delays, throttle execution, or give other threads a chance to run. Sleep temporarily moves the thread to the timed waiting state. Yield suggests to the scheduler that the current thread is willing to pause so other threads of equal priority can run. Yield does not guarantee any order or timing, and the thread may be scheduled again immediately. Together, these methods help control concurrency behavior, but using them correctly requires understanding locks, scheduling, and communication patterns in multi-threaded applications. Next, what is a thread pool and why is it used? A thread pool is a collection of pre-created reusable worker threads managed by the executor framework. Instead of creating a new thread each time a task needs to run, tasks are submitted to a queue and available threads pick them up for execution. This approach significantly improves performance because thread creation and destruction are expensive operations. Thread pools help manage system resources by controlling the maximum number of concurrent threads. This prevents applications from creating too many threads and overloading the CPU or memory. They also improve responsiveness because idle threads remain ready to execute tasks immediately without waiting for creation. The executor service interface provides different pool types such as fixed thread pools, cached thread pools, scheduled executors, and work stealing pools. They allow developers to choose the most efficient execution strategy based on workload. Thread pools are essential in web servers, microservices, batch processing, event-driven systems, and background task execution. They promote scalability, reduce latency, and ensure stable performance under heavy load. Next, what is Callable and Future in Java multithreading? Callable is an interface similar to Runnable but allows tasks to return a value and throw checked exceptions. Future represents the result of an asynchronous computation, providing methods to check completion, retrieve the output, or cancel the task. Together, they enable powerful asynchronous programming in Java. When you submit a callable to an executor service, it returns a future immediately. The main thread does not block at submission. Instead, it can continue other work. When the result is needed, calling future.get blocks until the callable finishes execution and returns the computed value. Callable is useful for tasks such as downloading files, invoking APIs, performing CPU-intensive operations, or running database queries in the background. Future allows tracking progress, handling timeouts, or canceling long-running tasks gracefully. This model improves responsiveness and helps build scalable, parallel applications without complex thread management. Next question. What are volatile variables and how do they differ from synchronized? A volatile variable ensures that every read of the variable is always fetched from main memory and every write is immediately written back. This guarantees visibility across threads, preventing one thread from reading a stale value cached by another. Volatile is useful for simple flags or status variables where operations are independent. However, volatile does not provide atomicity. If multiple threads modify a shared variable using non-atomic operations like increment, Volatile cannot prevent race conditions. In contrast, Synchronize enforces both visibility and atomicity by locking critical sections. It ensures that only one thread at a time modifies shared data, making it suitable for compound operations. Volatile is lightweight and faster, but limited to simple state sharing. Synchronize is heavier but essential for complex operations on shared objects. Choosing between the two depends on whether you need only visibility or both atomicity and mutual exclusion.